Oh, that's interesting. It changed on Monday. Okay, so we're in this issue. We're dealing with still section 1 from chapter 9, which is what they call molecular geometry. Let me make sure I've got the exact title. Move this out of the way. This little screen is too small. Molecular geometry, that's the name of it. Okay, so what we said yesterday was that we have this theory called the VSEPR theory, VSEPR, if you want to call it that. And what it suggests is that there are groups of electrons around a central atom, which we call electron domains. And those electron domains will move away from each other so as to minimize the repulsion of the electrons in those groups. So when that happens, the atoms attach to those electron domains, and so they will reflect, the shape of the molecule will reflect the distribution of those electrons. So what we said was that it was useful to have a little table, the number of electron domains. And so we started with 2, and then we had a shape, and we had an angle. And sometimes there's more than one angle. But if we had 2 electron domains, the distribution of those electron domains would be what we call linear. And the angle would be 180 degrees. And so here's a diagram of it. So your central atom is in the center, and then you have these electron domains, which we're representing as an atomic orbital, but it could be a single bond, a double bond, a triple bond, or a lone pair. They're as far apart as they can get. If you move up to 3, then it becomes trigonal planar. And so now the angle is reduced because there's more groups. So it's reduced to 120. And it looks kind of like a little propeller, like a 3-bladed propeller. Okay, it's flat. It's flat. There we go. It's flat, so it's 2-dimensional, so trigonal planar, little triangle. If you get up to 4, now it becomes 3-dimensional. And so that was called tetrahedral. And that was 109.5 degrees. And so again, here's your central atom. Now it's 3-dimensional, so we can represent it like this. So this one over here is going into the board, or into the plane that we're drawing on, and this one's coming out of the plane. Okay, and then these 2 are in the plane of the drawing. Okay, then you get to 5. 5 is actually a combination of 2 different shapes. It's a combination of these 2 shapes. So it's called trigonal bipyramid. Sometimes people will put an AL at the end. And this one has 2 angles. So it's either represented as 120, 180. Sometimes it's represented as 120, 90. Just depends who's doing it. So this one's 3-dimensional, just like the tetrahedral is. So it's like you have a linear, that's like a linear right there. And then you have one coming out, going in, and then one in the plane. So that's like these are called your equatorial right there in the center. So I put a little triangle there to represent that that's really your trigonal planar, is actually that middle part. And then the linear part is like this, a straight line through. Okay, so the 120 is in the equator, right? So it's the difference between those 2, for example. And then either 90 is coming up here, that would be 90. Or if you want to go all the way up to here, it's 180. So different people will represent it differently. Okay, and then the last one is octahedral. And this one is 90. It's generally described as 90. So this one has 6 groups. 1, 2, linear. 3, going into the plane, coming out of the plane, linear. 5, 6. So you got 6 groups. It's essentially you get a little square here in the middle. And then you have a straight line here. But if you rotate it, it's actually a straight line this way. And if you rotate it another way, it's a straight line through there. So those are all 90 degrees, and that's called octahedral. And then the Vespert model says that, look, you have these electron domains, and the atoms just attach to them. So if you had an atom attach over here and an atom attach over here, that would be linear. The molecule would be linear, right? If you had an atom attach here, and you had an atom attach here, and you had an atom attach there, then that would just be trigonoplanar. The molecule would be trigonoplanar. And then if you had, 4 attachments here, the molecule would be tetrahedral. But then we said there was this issue, which was, what if, let's say, for example, only 2 atoms attach here, not 3, but 2. Then what would happen is the shape of the molecule would not reflect, it wouldn't be linear. It would be taking up 2 of these orbitals, but not the third one. So what shape would we call that? And we said that was bent. That if you had 2 atoms and like a lone pair, that would give you a bent structure. So the shape of the molecule is not always the same as the shape of the electron domains, as the distributions of the electron domains. So that's why we had to have another table, which kind of gave us, everything about the shape of the molecules. The molecule is what we want to know. We're not that concerned in the long run with the electron domain. We want to know about the shape of the molecule, but the shape of the molecule is affected by the number of domains. So here's what we did. We said we would use a notation where we have a central atom, A, and some number of surrounding atoms, X. And then we said, okay, how many lone pairs are there on the central atom? Well, if there aren't any, then what happens is the shape of the molecule is exactly the same as the distribution of lone pair of electron domains. So you get a linear. If you had a central atom with 3 surrounding atoms and no lone pairs on the central atom, then that would be trigonal planar, and so forth and so on. So in other words, if there's no lone pairs on the central atom, oops, that was meant to be a 4. If there's no lone pairs on the central atom, then the shape of the molecule is essentially the same as the shape of the electron domains. So that's easy. So trigonal bipyramid. And again, sometimes people put AL at the end. And then AX6 is your octahedral. But what happens is, that's a 6. What happens is, if you have lone pairs on the central atom, that changes, it changes a lot. So here's what could happen, for example. You could have AX2, but you could have a lone pair. So we'll represent that lone pair as an E. And remember, it's on the central atom, not on the surrounding atoms. Okay? So when that happens, it's bent. And the angle is around 120. Okay? And let's think about why that's the case. Here's your central atom. You've got 2 electron domains and a third one. So there's your 3 domains. One is a lone pair. I'll represent that over here as a lone pair. And then the other 2 are bonding to atoms. So this is your X, and this is your X. And then this is your E, your lone pair. So what happens is the shape of the molecule is actually more, it's reflecting that of the trigonal planar. So it ends up being bent. Okay, so this is bent. And then same thing if you have 2 lone pairs. So this means 2 lone pairs on the central atom. It's also bent, but the angle is smaller. Here it's around 120 degrees. Here it's 104.5. Okay. So the example of this would be water. Water has 2 lone pairs on oxygen, 2 surrounding atoms. And so its angle is around 104.5. And we call that a bent structure. If you have 3 surrounding atoms and 1 lone pair on the central atom, this one is called trigonal pyramidal. Okay, trigonal pyramidal. And the angle there is about 107 degrees. And there are others. I'm not going to go through all of them right here, but there's, when you look at your table 9.2 in your textbook, it will give you all of the different possibilities. There's really about a dozen possibilities there. And we've gone through, 8 of them. So there's like 4 other possibilities other than those 8. Okay. All right. So let's do a little practice here. So what I'm going to do is I'm going to bring up Alex and let's see if we can find one. Okay. So here's one. So this is called predicting bond angles. Okay. All right, let's take a look. Let's see what this one looks like. So this one is SO3. And they want you to find the bond angles, okay? Now, here's how you go about it. When you're going to do these kinds of bond angle, it's a very specific question. What's the bond angle? But really, to answer that question, you have to do a full analysis. You have to do the Lewis structure, figure out what the arrangement of electron domains are, figure out what the arrangement of the atoms are, and then you figure it out. So don't be fooled into thinking, oh, I'm just going to look at the molecule and I'll get the angle out of it. The angle comes from the shape. The shape comes from the arrangement of atoms. The arrangement of atoms comes from the arrangement of electron domains, and the electron domains come from the Lewis structure. So you have to run it through each step. So step 1, you do the Lewis structure. So we have S with 3 oxygens. Okay, then we count up valence electrons. Sulfur is in group 6A, so is oxygen. So you've got 6 electrons for the sulfur and 6 electrons for each oxygen. So that's a total of 24 electrons. Now, we've already made 3 bonds, so we've already used 6. So we're down to 18. And so we put them around the surrounding atoms and get them up to 18. Okay, now the sulfur, so there's minus 18. The sulfur doesn't have enough electrons, right? It only has 6. So what do? We use one of the oxygen atoms and we push a pair of electrons to form a second bond. And that's going to give it's going to give sulfur an extra pair of electrons. So the way we represent that is the double-headed arrow. That tells us that we're forming a different Lewis structure. And so now we have a double bond to this oxygen. And of course, based on resonance back in chapter 8, we could use any of these oxygens instead of the one on the left, and that's fine. But you're going to get the same structure. You're going to get the same geometry. So it doesn't matter which oxygen you pick. Okay. All right. So now the sulfur has 8 electrons. We're pretty good. Now, some people might argue that you're going to do an extra bond to sulfur and its expanded octet, but that's not important for us right here. Okay. So here's our Lewis structure. So now what you do is you count up electron domains. So the number of electron domains, remember, a single bond, a double bond, and a triple bond all count as 1, as does a lone pair. Okay. So you've got a single bond, and a double bond. So that's a total of 3. So you have 3 electron domains. Okay. Now let's count up the number of surrounding atoms. 1 oxygen, 2 oxygens, 3. So it's X3, right? So it's really AX3. So now you ask yourself, okay, well, you have 3 electron domains and it's AX3 with 0 lone pairs, right? 0 lone pairs. You just go back to our previous table. The previous table was AX3 with 0 lone pairs. That was trigonal planar, right? That was trigonal planar. And so there you go. So now you know it's trigonal planar. Well, what's the angle for trigonal planar? 120 degrees. Okay. So really what's happening then is the sulfur is at the center, and you've got 3 oxygens attached to the sulfur via these electron domains. So here's your oxygens. And the angle's around 120 degrees. Now, I'm going to give you a little bit deeper analysis here. And this is kind of interesting. It turns out a double bond takes up a little more space than a single bond. Just a little bit. And so what happens is when you have a double bond, or a triple, but typically it's not an issue for a triple bond, what happens is it pushes the other atoms a little closer to each other because the double bond just takes up more space. So remember here how we have an oxygen that's a double bond? So if that were this one here, we would just say, hey, look, this is just going to take up a little more space. And so it's going to squeeze these 2 atoms a little closer. So it's going to be a little bit less than 120. So it might be like 117. It might be 118. But it's going to be a little bit less than 120. Okay. So it's essentially 120, but it's going to change it a little bit. Okay. So there you go. Let's take a look at another one. Oh, here's a good one. Okay, same thing. This one's PCl4 plus. Okay, and then for that previous example, you would just put 120. You don't have to worry about the 118, 117. It's essentially 120. That's the angle that you could report there. Okay, so here's PCl4 plus. Now remember, this is an ion, right? So when you draw the Lewis structure, you have to subtract an electron, because it's a positive charge. That means you've lost an electron. So phosphorus is at the center. You have 4 chlorines. Okay, now let's count up all of our electrons. Okay, we have 5 electrons for the phosphorus. That's in group 5A. So you got 5. Chlorines in group 7A. So you got 5 for the phosphorus and 7 for each of the chlorines. However, we got to subtract 1 electron. So I'm going to subtract 1. Remember I said a lot of these are even electrons. So what happens is PCl4 isn't very stable because it has an odd number of electrons. But PCl4 plus is somewhat stable, because it has an even number of electrons. So 28 plus 4 is 32. We've already made 4 bonds, so that's 8. So now you're down to 24, right? A bond is 2 electrons. Put 6 around each of the surrounding atoms. If you have any extra electrons, you put them on the central atom. Phosphorus is in the 3rd row, so it is possible for it to have more than 8. But this looks pretty good, actually, because I just used 24. We're all done. Remember, it is plus. So for the Lewis structure, we put brackets around it and a positive sign. Okay. So actually, looks like phosphorus is at 8. Each chlorine is at 8. It's positively charged. You know, it looks pretty good. That's actually, I don't think we have to go any further on the Lewis structure there. Doesn't look like we need any double bonds. Okay. So now what do? Now we count up a number of electron domains. So remember, a bond is an electron domain, a bond to an atom. So that's 4. And now let's do our little formula. We have a central atom, phosphorus, 4 surrounding atoms, X4, and then there's no lone pairs. Okay, so this is AX4 with no lone pairs. So we go back to our table, and that's called tetrahedral. Right? Tetrahedral is the case where you have AX4 with no lone pairs. Now, if it was AX4 with a lone pair, that's going to change it. If it was AX4 with two lone pairs, that would change it. Then you go back to that table and look that up. But here we go. This one right here is tetrahedral. The angle for tetrahedral, 109.5 degrees. Okay, so the bond angle for this one, we would predict to be 109.5. Yeah. There we go. 109.5. There we go. Good. SO3, PCl4 plus. That one's an easy one. Okay. I'm going to go over one that's a little different. Not a big difference, but a little bit. So with this one, they give us a molecule, CH2, Cl2. Okay, so this one's a little different, right? It doesn't have all the same surrounding atoms. So remember what we said earlier when you're doing organic molecules. The carbon goes at the center, and pretty much everything that comes after it is surrounding the carbon. So CH2Cl2 is just C at the center with two hydrogens and two chlorines. See, carbon's an amazing element, an amazing atom. It's really what's responsible for life is carbon atom compared to all the other elements. The other elements are, of course, required, but carbon, what it does is it forms bonds with almost everything. It sticks to so many different elements. It will bond to chlorine, to hydrogen, to oxygen, to phosphorus, to nitrogen, to sulfur, but it does it in a way that allows it to form more than one bond or more than two bonds. It can form up to four bonds. And so by being able to form four bonds, up to four bonds to all these different elements, it just gives it an enormous diversity of possibilities that other elements just don't have. So oxygen, for example, generally only forms two bonds, and that just lowers the possible types of molecules you can have. Chlorine generally only can form one bond, only one atom. It only bonds to one atom. So there's really no diversity in terms of what chlorine can do. But carbon is right at the position in the periodic table, right in the middle in a sense. It's in the middle of the nonmetals. So it just allows it the maximum number of possible bonds. So when you see these formulas that have carbon in them, essentially just put everything around the carbon. Okay. If you see more than one carbon, attach the carbons to each other in a straight line, and then you'll be okay. So let's go through the Lewis structure. Carbon is in group 4A. Hydrogen is in group 1A, and chlorine is in group 7A. So we have 4 electrons for the carbon, 1 for each hydrogen, but there's 2 of them, and then 7 for the chlorine. So 14, 16, you got 20 electrons, right? Is that right? 14, 16, 18, 20. We've already used 8. We've done 4 bonds. Okay. Hydrogen duet rule. So don't add any electrons to the hydrogen, but the chlorine is the octet rule. So you put 6 there, and you put 6 there. So there's your 12. 0 electrons, right? So we're done. We got the Lewis structure. Carbon has 8, octet rule. Chlorine has 8, octet rule. Remember, the octet rule only gets violated if the atom is the central atom. Surrounding atoms do not generally have more or fewer than 8, unless it's hydrogen, of course. So what do? Let's count up electron domains. Those are the number of domains around the central atom. 1, 2, 3, 4. So the arrangement of the electron domains is going to be tetrahedral. And then we look up at the chemical formula. We have one central atom, 4 surrounding atoms. So notice what I'm doing here. I'm counting the chlorine and the hydrogen the same. They essentially are all just surrounding atoms. So we don't have to worry that one's a chlorine and one's a hydrogen, so that's going to change the shape. The shape is dependent on the attachments, where they're attached. So if you attach a chlorine or you attach a hydrogen, that doesn't change the shape. So it's just AX4. You can treat the chlorine just like it was another hydrogen. No lone pairs, right? So that's tetrahedral. And that's 109.5 degrees. Okay. So here in this question, they ask you to figure out what the angles are. And so they ask you for like, what's the angle between the carbon and the hydrogen? So here's your hydrogen. So carbon, okay, you can't talk about the angle between 2 atoms. You have to talk about the angle between 3 atoms. Because an angle is the bond angle, meaning what is the angle if you go from one atom, the center is the central atom, and you go across to the next surrounding atom? That's what a bond angle is. And so based on what we have here, that angle is 109.5 degrees. Okay, now what about the chlorine? Well, it's 4 of them, so I'm going to attach a chlorine over here. Chlorine's bigger than hydrogen, and it's bigger than, actually it's not bigger than carbon, it's smaller than carbon, but it's bigger than hydrogen. So we're going to draw it like this. Okay, actually carbon's bigger. Okay, and so same thing. Now it's difficult for you to see because I'm trying to draw a 3-dimensional thing, but all the angles are 109.5 degrees. They're all 109.5. So there's just a perspective here. These look closer because we're drawing it in 2D. But it's actually swept out as 109.5. Okay, so tetrahedral 109.5. Let's see if there's any that are significantly different. Doesn't look like it. Looks like they're all pretty much the same. Oh, here's one. Let's try this one. This one is COF2. Okay, now that's an interesting question, COF2. Same idea. Notice you have carbon. And then you got O and F2. So what's the arrangement going to be? Again, if you have carbon with other elements like hydrogen, oxygen, fluorine, chlorine, put them all around the carbon. So you take the carbon, you put it at the center. You take the oxygen, you put it attached. Take 2 of the fluorines, right? Take both fluorines and attach them. So don't do something like this, COF2. Don't do that. If you have carbon, put it at the center and attach everything to the carbon. Okay, and that's what carbon does. That's why it's such a powerful element in terms of biology, okay, and other fields as well. So let's count up electrons. Carbon's in 4A, oxygen's in 6A, fluorine is in 7A. So you got 4 plus 6. There's 2 of the fluorines. So you got 24. Okay, we've already used 6. So you got 18. So put them on the surrounding atoms, get them up to 8. The pattern here is that because you start off with a single bond to the surrounding atoms, it's always going to take 3 lone pairs to get it up to 8 because you got 2 with the bond. So 3 lone pairs will give you a total of 8. So here it worked out nicely. But the problem is here, the carbon only has 6. So now we have a question. Which atom are we going to donate the lone pair to the carbon to form a second bond? And the real determining factor is formal charge. So let me show you what happens. Suppose I said I'm going to take the fluorine and do it with that one. Upon looking at it, it seems to work. But I'm going to warn you, this is not the correct Lewis structure. And here's why. Let's go back to chapter 8, formal charge. If you do a formal charge calculation for fluorine, you take the number of valence electrons. So this is formal charge. And you subtract the number of electrons in the lone pairs, so that's 4. Remember, we're subtracting associated electrons, we called it, valence electrons minus associated. And you got 2 bonds. Remember, each bond is only 1 electron in the formal charge calculation. So you get 7 minus 6, which is +1. So you have a +1 formal charge here. And then if you do a formal charge on the oxygen, for the oxygen, it's 6 minus 3 lone pairs. So that's 6 electrons right there and a single bond. So you get 6 minus 7, which is -1. So you have a formal charge of -1 here. And what we said was formal charges of 0 are better. So let me do it a second way. I'm going to do it to the oxygen. I'm going to do the second bond to the oxygen instead of fluorine. Oops. Okay. Now, if you do the formal charge for fluorine, it's 7 valence electrons minus associated electrons, 3 lone pairs, plus 1 bond. You get 0. Now we do the oxygen. 6 minus 2 lone pairs, 2 bonds. Remember, a bond you only count as 1 in formal charge, and a lone pair you count as 2. So 0 here. Better, right? This one's better. When you have formal charges that are closer to 0, it's better. So how do we know? Like, do we have to go through the formal charge to calculate this every time? And the answer is technically yes, but there is a little shorthand notation. And so let me show it to you. I'll come back to this in a minute. And here, let me show you what happens. If you want the formal charge to be 0, so this is to get a 0 formal charge, the number of bonds that the elements in group 7A have is 1. Okay, so 1 bond. That will give them a 0 formal charge. Okay, that's easy to remember. 1 bond gives it a 0 formal charge. If you do group 6A, oxygen, sulfur, selenium, and tellurium, for this one, it's 2 bonds. Okay, I'm sorry, I'm running out of, let me write it down here. I didn't really organize that well. So 1 bond, and when you do 1 bond, you get 3 lone pairs, because you got the octet rule. With group 6A, it's 2 bonds and 2 lone pairs. Okay. When you do group 5A, nitrogen, phosphorus, arsenic, I guess antimony's below that too, but let's not worry about that one. It's 3 bonds and 1 lone pair. That's what's going to give them 0 formal charges. And then carbon is group 4A. So carbon and silicon, 4 bonds and 0 lone pairs. So when you draw Lewis structures, if you remember that, oh yeah, group 7A, it's only going to have 1 bond. Oh, group 6A, it's going to have 2 bonds. Now here's what happens. you come back to this Lewis structure, and this is really what organic chemists do. They're good at this. They recognize immediately where the double bond is going to be and where the single bond is going to be. But you can learn it very quickly. You'll learn it like immediately when you take organic, and you can learn it right now. Here's our situation. The carbon has 6 electrons. It needs to have 8. It needs another bond, right? Another bond will give it 8 electrons. Which atom is going to do it? Well, we want to have 0 formal charges. And so fluorine, 1 bond gives it a formal charge of 0. So an extra bond to fluorine that's not going to give fluorine a formal charge of 0. But what about oxygen? Oxygen, its 2 bonds will give it a formal charge of 0. So let's pick the oxygen. Let's put our second bond here. Oops, sorry, didn't draw that well. Let's put it on here. Oops, erase something too. There we go. Oh, I keep drawing it over toward the fluorine. Sorry. There we go. Okay, so let's take the oxygen, put a second bond to the carbon, and now your formal charge on the oxygen is going to be 0. So when you're trying to find double bonds, oxygen is more likely to have a double bond than fluorine will never have double bonds in these structures. Oxygen can have a double bond. In fact, oxygen can very often be very happy with the double bond because that gives it a formal charge of 0. Okay, so that could be helpful for you there. Okay, all right. So now we have the Lewis structure. There's our Lewis structure. So how do we get the shape of the molecule, the bond angle, right? We're doing bond angles here. Well, let's do our number of electron domains. We have 1 here, and 1 here, right? Remember, a double bond is 1 domain, it's 2 bonds, but 1 domain because they're pointing in the same direction. So that's 3. So the angles of the electron domains are going to be based on trigonal planar. That's 120. So now let's look at the formula. We have 1 central atom, 3 surrounding atoms, right? AX3, no lone pairs. Trigonal planar. And that's 120 degrees. Okay. So now we know our angle is 120. So what does that mean? Essentially what it means is you've got the carbon at the center. You've got a double bond, which I'm going to represent as an electron domain, coming over here to the oxygen. And then you've got 2 fluorine atoms. Right here. Right? And that angle is 120 degrees. There you go. We're done. We got 120. That's, they don't ask you for the shape, but it's trigonal planar. Arguably, the double bond takes up a little more space. So the bond angle between the fluorine atoms might be a little tiny less than 120, might be 118. The angle between the oxygen and the fluorine might be a little more than 120, like 122. But for the most part, we ignore that. We don't need to worry about the real precise measurements of what those angles are. It's essentially 120 degrees. Okay. So let me close that. Okay. Let me show you a second type of problem that they have you do. This one's a little more abstract. They're not actually showing you real molecules. They're just showing you little diagrams, and then you're supposed to figure it out. Some of them are real, actually, taking a look at here. So let me show you an example, this one. This one is called Predicting Bond Angles of Small Organic Molecules. Okay. So what they do is they show you a little molecule. And they're showing you the Lewis structure. So they've already drawn the Lewis structure for you. And they do a pretty decent job of drawing it pretty big so that you can kind of see what's happening. And then what they do is they ask you to figure out a couple of the angles. So the first one in this one they want you to figure out is the angle between here and here. And they call that angle A. And then the second one is between here and here. And they call that angle B. Okay, so what are those particular angles? So here's how you approach it. Okay, in these small organic, remember these are small, right? A large organic molecule has millions of atoms in it, right? A DNA molecule has millions of atoms in it. A chromosome, for example, if you want to think of that as a molecule. This only has 4 atoms. But even in this 4-atom molecule, there's more than one central atom, right? A central atom is an atom that has more than one atom attached to it. The oxygen has 2 atoms attached to it, so it's a central atom. The carbon has 2 atoms attached to it, so it's also a central atom. So that's why there's 2 angles. The bond angle is relative to the central atom. So if oxygen is a central atom, there's going to be an angle between the hydrogen to the carbon. Mathematically, you think of the central atom as the vertex. And so imagine that we sweep out an angle like this. There's your angle theta, right? Here's your central atom. Here's your surrounding atom. Here's the next surrounding atom. What's the angle between these 3 points? That's essentially what we're doing here. Okay. So let's do angle A first. So here's how you approach it. You look at the central atom first. So the central atom for angle A is oxygen. That's your central atom. Count up everything around it. What is attached to that oxygen? The oxygen has a bond to a hydrogen, a bond to a carbon. So we're going to write that as AX2, right? 2 surrounding atoms, right? So the surrounding atoms in the case of the oxygen are the atoms attached to the oxygen. So there's only 2 atoms attached to it. The nitrogen is not attached to the oxygen, so we don't worry about that one. We're just going to worry about the hydrogen and the carbon because those are the 2 atoms that are attached to it. Okay. Now we write down the number of lone pairs around the central atom. There's 1 lone pair at the top and 1 at the bottom. So we write that as E2. AX2, E2, right? That's the notation we're using. A is the central atom. X is the surrounding atom. Doesn't matter if it's a different type of surrounding atom. And then E is the lone pair on the central atom. If there's more than 1, it's E2. If there were 3 lone pairs, it would be E3. Okay. So what did we get? That goes back to that table 9.2. That's going to be bent. Right? It's actually like water. And so the bent angle was 104.5 degrees. Okay, if it was AX2E2, it was 104. If it was AX2E, then it was 120, but that's back in our table. Now let's do angle B. For angle B, the central atom is carbon. That's your central atom right there. So what does carbon have? It has 2 surrounding atoms and no lone pairs. AX2, no lone pairs. I'll put that in parentheses. Okay. Doesn't matter that nitrogen has a lone pair. Nitrogen is not the central atom. We're only counting what's around the central atom. That's a fundamental idea of this VSEPR theory, is that we're looking at it from the perspective of the central atom. So AX2 with no lone pairs, that's linear. And that's 180 degrees. Okay. So I'm going to draw the molecule. I'm going to try to draw the molecule. They don't ask you to do it, But I want to show you what it looks like. You get something like this. So the carbon is linear, right? What we said was that angle B was linear. So it's a straight line, just like it is in the Lewis structure, actually. But then it's bent around the oxygen. So how do we do that? We do it like this. Hydrogen's smaller, so I'll draw a little smaller, right? So here, this is what you get. You get a straight line here. That's linear. And then around the oxygen, it's bent. A little more than a right angle, 104.5. So around the carbon, it's linear, 180, straight line. And then around the oxygen, it's bent. Again, you don't have to draw that picture. They just want you to identify what the angles are, angle A and angle B. So that would be 104.5 and 180. But that's what it would look like geometrically. Okay. Let's see if I can find another one. Here's one. So same idea. We're going to do, this is actually an actual molecule. This is methanol. So this is an actual molecule, and they give you the Lewis structure. Okay, and then they have, again, two angles they want you to do. So the first angle is between, okay, so it's around the carbon, so it's here. So that's angle A. And then the second one is around oxygen. Okay, so notice we wouldn't talk about the bond angle around hydrogen because hydrogen is not a central atom. Every hydrogen is only attached to one atom, so it's not a central atom. To be a central atom, you have to be attached to more than one atom. So only the carbon and the oxygen are central atoms. So carbon, let's do bond A. So bond A is around the carbon. So that's right here, right? Right there. Okay, so what do we do? It's very simple. You go back to your table 9.2. You take the central atom, which is A, count up the number of atoms that are directly attached to that atom. Oxygen is attached to carbon. So are three of the hydrogens, but one of the hydrogens is not. So that means there's 4 atoms attached to the carbon, 3 hydrogens and 1 oxygen. So that's 4. So that's AX4. There aren't any lone pairs on the carbon. So there's no lone pairs. So immediately we can say that's tetrahedral. And our angle is 109.5. So there we go. Got that one. Got angle A. Part B. Well, that's around the oxygen. That's the angle around the oxygen, right? So how do we deal with that? Well, the oxygen is bonded to a carbon and a hydrogen. So that's AX2. It's not bonded to these other hydrogens, so we can ignore those. And then it's got 2 lone pairs, so E2. 2 lone pairs. And we did that before. That's bent. 104.5 degrees. So now we have our 2 angles. For the carbon, it's 109.5, which is very common for carbon. Tetrahedral is common for carbon. And then around the oxygen is bent. Very common for oxygen. Oxygen is typically bent. That's why water is bent around the hydrogen, around the oxygen. Okay. So this one's a little more difficult to draw, but I'm going to try. I'll put the carbon over here. And it's tetrahedral around it. So here's your hydrogens. CH3, right? That's CH3. That's very common in chemistry. CH3 is very common. And now we're attached to the oxygen, right? And the oxygen is bent. So here I'm gonna put the oxygen here. And it's bent. So that means the hydrogen is down like this, right? So it's bent here. And then this right here is tetrahedral. They often refer to this as tetrahedral carbon because carbon is often tetrahedral. And knowing that it's tetrahedral tells you a lot about its properties and structure and that sort of thing. Okay. Let's see, we got time. Let's do one more. Okay, so here's one. Again, this is an actual molecule. This one looks like it's propene. So CH2. Three carbons now, right? So we actually have, they're only going to have you do two angles. Okay, so they're not going to have you do all three, but we could do all three. Actually, they do something kind of interesting here. So they have you do this angle here. And they call that angle A. And then they have you do this angle here, which is angle B. Now, this is a trick question in a way, because they are doing two different angles, A and B, but it turns out the angle is going to be the same for both of them because they're around the central atom, the same central atom. Both of those angles are around the carbon, the same carbon atom. So let's take a look. Okay, we only need to worry about this carbon now. They didn't ask us for any angles around the second carbon or the third carbon. By the way, we often number these. We would call the first carbon C1, and then we would call the second one C2, and then we would call the third one C3. You number them, and you start with the double bond, okay? So let's take a look at that carbon. That carbon has two angles. Let's do A. So it's an atom, a central atom attached to two hydrogens in another carbon. So that's AX3, right? Doesn't matter that it's a different element. Hydrogen is a different element than carbon, but they're all surrounding atoms on that C1 atom, right? No lone pairs. Well, that's trigonal planar. And that's 120. Isn't that cool? Now let's do angle B. Angle B is the bond angle between the hydrogen. So the carbon's at the center. You're sweeping from the hydrogen down to the carbon. Okay. Well, same thing. Do the same thing. You have one central atom, and you have three surrounding atoms, and no lone pairs. So it's trigonal planar again. It's a trick. It's the same angle. Okay. Now, arguably, the double bond might change the angle a little bit. A double bond takes up a little more space. So maybe angle B is a little under, I'm sorry, angle B would be a little more than 120, like 121, 122. Angle A is a little bit closer, so maybe 118. But it actually tells you, don't worry about the small differences, that they have different sizes, the lone pairs versus double bonds and single bonds. Don't worry about that. Just do the basic structure. The basic structure is AX3 is going to be 120 degrees. Okay. Now, once you do these, you can actually do them very quickly. An organic chemist student, when you're in your first semester of organic chemistry, very quickly you'll learn this, like within a week or two. You'll be like, oh, okay, let's do this carbon right here. It's an atom, so it's A. It's got 1, 2, 3 attached atoms. AX3, no lone pairs, so 120 degrees. Let's do this carbon over here. This carbon over here has 1, 2, 3, 4 atoms. AX4. AX4 is tetrahedral, 109.5 degrees. So you would know, oh, tetrahedral, trigonal planar, and then trigonal planar. Okay. And then you would draw it, But in here, all you got to do is figure out what the basic angles are in your set. Okay. All right. I think I have time for maybe one more. The last problem in section 1 is having you do Let's do this one. Doing this one, this is called predicting and naming the molecules with one central atom. So predicting and naming the shape. Okay. So in this one, they give you the formula. And then they want the two-word phrase that names it. Spelling is important here. Make sure you get your spelling right. And then they want the bond angle. And then they tell you it's in degrees. Okay, so let's figure this one out. Simple molecule, a simple ion, right? Okay. Excellent. Okay, so here, let's go through it. We got iodine is the central atom. It's got 4 chlorines. So see what I'm doing? I'm drawing the Lewis structure, right? That's what we said. Let's count up electrons. Iodine is in group 7A, so is chlorine. So you got 7 for the iodine, 7 for each of the chlorines, but then it's also negative. Remember, if it's negative, you add 1. So you get 36 electrons, right? So that's 28 plus 8 is 36. Okay, we've already used 8. So now we're down to 28. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. It's negative, so make sure you put your bracket negative there, okay? 28. Oops, sorry, that's 24. So now you got 4 left. I did 24 there. So what do? Once you get the surrounding up to 8, if there's any extra, you put them on the central atom. All right. So now we got it, okay? Still very straightforward. Here's what you do. Again, let's count up the electron domains. We have 4 surrounding atoms and 2 lone pairs, so that's 6. And now let's do our formula. We have a central atom, 4 surrounding atoms, and 2 lone pairs, right? That's important. The lone pairs are what change it. If there were no lone pairs and it was just AX6, it would be octahedral. If there were no lone pairs and it was AX4, that'd be tetrahedral. But there's 2 lone pairs. That changes the shape. This is an interesting one. It's called square planar. And it's 90 degrees. Every angle is 90 degrees. So AX4E2, again, that's in table 9.2. It's square planar. Square planar is a famous structure because there's a famous molecule that was discovered in the 1960s that had anti-cancer properties. So it was the first, really one of the first synthetic compounds that they found could like reduce the size of a tumor. And that molecule is still sold today. It's used for specific types of cancers and chemotherapy. And it's called cisplatin. And so if you type in cisplatin into Google, you'll find that chemists like to talk about it because it's square planar, but also it's a medical compound. So derivatives of it are used even to this day. So the idea then is square planar. What's a square planar? I haven't really shown you that structure. Square planar is cool. Oops. Oh, okay. Sorry. Okay, let's try now. There we go. So square planar is AX2E2. Okay, and it's 90 degrees. So here's what you have. You have the central atom is attached to 4 surrounding atoms in the form of a square. And as we know, a square is 2-dimensional, right? A box is 3-dimensional, but a square is only 2-dimensional. So you get this little square. Now it kind of looks a little bit like a rectangle here, but I didn't quite draw it perfectly, but it's essentially a square. And each of those angles is 90 degrees. Okay, so that particular one, the famous anti-cancer or anti-mutagen, what is it called? An anti-tumor is, let me see if I can get it right. It has a platinum atom at the center, actually. And then if I got this right, it has 2 chlorine atoms that are on the same side. And then it has 2 ammonia molecules, NH3, that are on the same side. Okay, so it's a little square. So this is called cisplatin. The cis referring to same side. So what that means is the chlorines are on the same side. So if I put them on opposite sides, so if I put a chlorine here and an ammonia on the same side, and then a chlorine on the other side, and an ammonia on this side. So now what happens is these chlorine atoms are on the opposite sides of the platinum. These ammonia molecules are on opposite sides of the platinum. So this is called transplatin. Trans is opposite side. Cisplatin is, that means that the atoms are on the same side. Okay, so that's cool. So that's a square planar. So in that particular problem, all you have to do is just give the name, which would be square planar. That's 2 words. Make sure you spell it right. Make sure you put a space between the 2 words. And then the angle. You just have to put what the angle is. So for this one, the angle would be 90 degrees. Okay. So that is the last topic from section 9.1. Most, there's a bunch of 9.1 because it kind of takes you step by step doing more and more and more complicated problems. So for 9.1, it's actually like 7 different topics. So tomorrow, what we'll do is we're just going to look at a really simple topic called polarity, molecular geometry and polarity. That's 9.2. And then we'll work on the next topic, which is hybridization. Okay. So have a great day. And I hope everything's going well. And I hope you're getting registered for your next courses, or you are graduating. That would be great too. And I will talk to you later.
Thank you.
Thank you.
Bye-bye.